In this lecture, we want to show how cohomology comes naturally from homology. So we start with the chain complex in homology. So this is a chain complex. These are the boundary maps given to us, and the kernel of this map contains the image of this map. So that's how this becomes a chain complex. And as we have explained in previous lectures, because of this we can compute homology. So homology at the ith point is kernel of this partial I, that is the arrow going out, modulo out the image of partial I plus 1. So for example, if you want to compute h2, so you have to compute it here. So kernel of the arrow going out of this c2, so you have kernel of this partial 2 over image of this partial 3, so I over I plus 1 at the ith point. Similarly, you can have h3 here, kernel of this partial 3 over image of partial 4. So for cohomology, we write our chain complex like this. So the arrows are reversed. So here we are going from 3 to 2 to 1. Here we are going from 1 to 2 to 3. So here indices are decreasing. Here the indices are increasing. Again, the definition remains the same. You again have kernel of the arrow going out, modulo out the image of the arrow coming in. So for example, you want to compute the cohomology group here. So that is nothing but kernel of the arrow going out, which is kernel of this D2 over image of this D1. So again, you can compute like this. So same procedure, kernel of arrow going out. So this is arrow out over arrow in. Here also arrow out over arrow in. So kernel of arrow out over image of arrow in. So these groups or these modules, this is a co-chain complex. This is obtained from the chain complex here by applying the home functor. So you apply this functor home integers. So you apply this functor to here. Now this functor is contravariant. So this functor is contravariant, and therefore it reverses the arrows. So you apply this functor here, it reverses the arrows like this, and these are precisely these maps. So this is our D1, this is our D2, D3. So in general, we always forget the indices, because in order to compute homology or cohomology, you just look at arrow out over arrow in. So if you want to compute h2, you just say, okay, it is kernel of t over image of t, and because we immediately know we are talking about this t as an arrow which is going out of this c2, and image is of the arrow coming in. So now we want to understand these maps home or this contravariant functor visually. So we have to define this d in terms of this partial. So first we have to understand how does this home look like. So home is nothing but this set of maps from this C1 here to Z, and this home C2Z is set of maps from C2 to Z. So we have to define this D and connect it with this partial here. So you have F here, and we want to map this F, which is an element of home C1 Z2, some G right here via this D. So let us see this. So we are going to map this F to G via this map D. So what is this F? So this morphisms from C1 to Z, they are just maps from C1 to Z. So this F is nothing but an arrow from C1 to Z. So this is the morphism. So this G is nothing but an arrow from C2 to Z. So this is our G. So D maps F to G. So we have to define this D here. In fact, we have to relate it to this partial here. So the first thing is, what is the natural relationship between G and F? So that is just this triangle here. So this triangle is commuting. So this triangle is commuting means going from here to here, that is G is equal to, first apply this partial and then you apply F. So this is the natural map, as you can see. So we are just doing this thing. So, and this is precisely what should be the definition of D, because this is the map which relates F and G. So easiest way to relate f and g is commutativity of this triangle. So that is precisely how we define d of f. So you apply d to f. So this is g. Precisely if d of f is, first apply partial and then you apply f. So you define d of f as, so this is defined as f and partial. So first apply partial and then f. First apply this partial map and then f. So partial and f gives you g. That gives you g precisely because of commutativity of this triangle. So now we have defined this map D. So D will take f to g via the commutativity of this triangle. So now a natural question arises, how are these homology and cohomology groups are related? So these are related via this universal coefficient theorem. So this homology group here, this K is our simplicial complex, whatever chain complex we are talking about, whether it is complex projective space or real projective space, Klein-Bottle torus. This could be any CW complex or simplicial complex. So this is iso to home of this homology group. So you have homology here, and then we have this X and homology again here. So you feed in the homology groups here and here, you get the cohomology group here. Now this home is just what we have in algebra, set of homomorphisms. This X is a derived functor, and to properly understand it, you have to see the lectures on homological algebra. But we can use this home and X directly as a black box to compute things. So let us see an example of how to compute cohomology using this formula right here. So we want to use this formula as a black box to compute cohomology from our homology groups. So a bunch of formula here are this home of z comma z is just z. So z modulo mz, z is 0 for home. Then home of z a z, z b z is z and z, where n is greatest common divisor of both a and b. So a and b are integers here, m is an integer. Then home of a direct sum b, this again integers, is home a z direct sum with home b z. Then x, we said we can use it as a black box. So z by n z, z is z and z here. Then x of the z and z is 0. X of a, this direct sum with b z is x of a direct sum with x of b and z. So there are more examples like this. In fact, more of these properties are discussed in the playlist Cohomology. So after watching this video, you can actually directly go to the playlist in Cohomology and see more of these properties of home and X mentioned. So now we will use this to compute an example. So this is the homology for Rpn. So if p is 0, it is integers. It is this z over 2z if p is odd. So if p is even, then it is 0. Now this n here could be even or odd. So if you're choosing this n to be even, then the homology would be 0. If this n is odd, then the homology would be integers. So from here we want to imply this cohomology here, which we will compute using this formula. So this is given to us, and we have computed the homology of Rpn using cellular complex or CW complex before. So the first thing we do is we copy this formula right here. So we are just making it simpler. We are just getting rid of this k here, because this k represents the simplicial complex or CW complex, and we know we are computing this example here. So we rewrite it like this. Now once we have rewritten it like this, let us start computing the cohomology groups. So we want to compute this cohomology group at 0th position. So this p is 0. So you put 0 here, and you have -1 here, because 0 minus 1 is -1 integer. So there is nothing -1 here. So this we are just going to take it as 0. So home of h0z. So what is this h0? So when p is 0, it is just integers right here. So h0 here is integers. So that's what we write here, hom z comma z, so it gives you integers. So for first h0, for p0 you get integers. So now we come to h1. So again you use this formula, instead of p you write h1, so cohomology at this 1. So this will, again you get homology group here 1, x of 1 less p minus 1, 1 minus 1 is 0, this. So what is this h1? So look here, this p for 1 is odd, so odd, so z by 2z. So this h1 is z by 2z. What is h0? h0 for p0 it is integers, so you get this. Now look at this result, x z z is 0, so this is 0. For this you look at this, because m is 2 now, so this is also 0, so this is also 0. So h1 becomes 0. So for p odd it is 0, so you can compute h3, h5 and so on. Same result will keep on repeating itself. So because you will keep getting odd here, so this term will become 0 and the second term will also become 0. Now for p even, for say h2, you have hom h2z, again this formula, p is 2 and p minus 1 here, so h1. So we are copying this down. So what is h2? So for p even you have 0, so this homology group here is 0. What about h1? h1 is 1 is odd, so you have z by 2z, so you have this. So hom 0z, this is obviously 0, and again for this we use this result here, so you get z by 2z. So we can do this. So you have seen for 1 it is 0, for 2 it is this, so you can do this for all odd and even. Now we come to this n. So the first thing is that this n is even, so here the n is even. In this case n is even. So if n is even, then you can just copy this here. This n minus 1 would be odd, and then z. So for even, you know n even, this is 0, so you put in 0 here, this will be 0. For this odd, you have odd here, this is z over 2z, so this is z 2z. So again x of this, use this result here, this is here z by 2z. So for n even you get this, so this n is even. What if the dimension of your manifold is odd? Again you have the same formula here, but now you have n minus 1 would be even, so hom h n z x this. So now you have hom z z because odd, so n odd you have integers here. So this was less than n. For n odd, for this dimension here, this is integers, so you have integers here. And for even, because even is going to be less than the dimension, you have 0, so you have 0 here, so this is 0, and this will just give you integers from the first result. So we have been able to compute the cohomology groups of RPN using the homology groups via this formula here.